Hi everyone, here are your section 4.8 notes, which is getting us into the inverse of trig functions. Now remember that a function is going to be one-to-one if it can pass the horizontal line test. If it does pass the horizontal line test, then its inverse relation will also be a function. So for sine, cosine, and tangent, if you think about those curves, they wouldn't clearly pass the horizontal line test, so we need to restrict the domains for each of those functions. And these are the following properties that we are going to be discovering. And we'll get into those in further detail, but there they are all in one straight shot list. Okay, so remember that a function will have an inverse if it is a one-to-one function. So it needs to be one-to-one in order for a function to have an inverse. That would be a function also. My pen's not turning on. There we go. Okay, so 1, 2, 1. Functions are going to be one-to-one if they have one x value for every y value, and a function f is function notation of f of x, and there's our inverse function notation, would have the following characteristics. So when you do a composition, if you guys remember back in Algebra 1, or Algebra 2, when you did compositions of functions, you can attest to check for inverses of each other is if you do a composition of a function and its inverse, and its output ends up being x, which is all those properties up there in that top table are showing. They're showing compositions of functions, trig functions with their inverses, with the resulting function being an x. So whenever you plug in the original function into your inverse, then every x needs to be in the domain of f. And then if you put your inverse into the original, would be equal to x, then for every x, the domain would have to be in the inverse of, or the domain of the inverse function. If you just remember, for all functions and inverses, the domain of the f is going to be equal to the range of its inverse, and then the range of the original is going to end up being the domain of its inverse. The graph of f and its inverse will be symmetric with respect to the line y equals x. And then if a function is y equals f of x has an inverse, then remember we flip-flop the y and the x's when solving for inverses. You put the x in place of y and the y in place of x, and then here would be our solution. So then the solution of this equation would be whatever your y is equal to for the inverse of function f. Okay. So let's go ahead and jump into our sine function and its inverse. So let's go ahead and plot the sine. It's requesting to -2 to +2 pi, but we don't have enough space to the left, so that's not going to work. So remember, sine starts at 0, max, intercept, min, intercept, max, intercept, going the other way. Gives us this graph, right? So this is half a pi, this is pi, and this is going to be 2 pi. Yeah. Okay, so this is at -half a pi. So, is it one-to-one? No, clearly does not pass the horizontal line test. So what we're going to do is we're going to restrict the domain so the graph will pass the horizontal line test. So if we think about the range of the sine function, that goes from -1 to 1. And remember, your range of the original function should be your domain of its inverse. So where are my values at -1 and 1? So if my domain is -1 and 1, what would be the y? Well, where are we at -1? Well, I'm at a -1 here. I'm at a -1 here. I'm at a -1 here. We're going to stick to working within the origin because 0, 0 is just a really nice point. So we're going to use, so at -1 we're at -half a pi, and at 1 we're at +half a pi. So remember, flip-flop your range and your domain for the original function to its inverse. So now my x values, my domain for its inverse, are going to have to be between -1 and 1, and the output has to be between -half a pi and +half a pi. So what does that look like in a graph? So if we think about my ordered pairs, well, the inverse of 0, 0, 0, 0. We have an ordered pair of half a pi, comma 1. So the inverse of that would be 1/2 a pi. So at 1, I'm going to put my 1 here just so I can spread it out. There's -1. We're going to be at half a pi. I don't know, put half a pi there, that'll look good. 0, 0. And then at negative half a pi, we were at -1, so the inverse of that would be -1, negative half a pi, which puts us down here. So what does that look like as a curve? Looks something like that. If you were to go graph it on your graphing calculator, you would go to y equals, and then you hit second and then sine to get your inverse, and then x. And I'm going to do a zoom 6 because I was playing around with it. So you can kind of see there's your curve in there occurring between negative half a pi and positive half a pi. Okay, so now we're going to do some evaluating. So remember that y equals inverse sine of x means x equals sine of y, where x needs to be between -1 and 1, and your y needs to be between negative half a pi and half a pi. So we're going to use this information to find the exact values of the following problems. Okay, so keeping in mind, my output needs to be between that. So if you think about your unit circle, right, where is negative half a pi? It's down here. Half a pi is there. So I can only work right now between quadrants 1 and 2. All right, so now let's reevaluate this. So if I set this equal to y, like we have here, then my equation becomes x equals, which in this case my x is 1. So sine of y needs to equal 1. So when is my sine equal to 1? Well, remember, sine is your y value of your ordered pairs. So that's up here, 0, 1. So half a pi. Okay, so now let's do the same thing for -1/2. So -1/2. So now not that I'm cheating, I want you guys to use your unit circle. I'm pulling up my unit circle, and I'm looking in quadrant 1 and quadrant 2, or quadrant 4. Now my sine needs to be negative. Well, in quadrant 1, they're all positive. In quadrant 2, sine is. In quadrant 3, tangent is. And in quadrant 4, cosine is. So I need my sine to be negative. So it's not going to be negative in quadrant 1, but it is going to be negative in quadrant 4. Because remember, I'm limited to this half of my unit circle. So now I'm going to look on my unit circle to see where do I have my y coordinate at -1/2. Well, it's going to be at positive √3/2, -1/2. And my radians on that is 11 pi over 6. Well, 11 pi over 6 is this whole entire angle. That's not between negative half a pi and positive half a pi. But this angle right here is, so what is that angle? Well, it's negative pi over 6. Because how many extra 6 do you need to get to 2? So 11/6 plus 1/6 would get you to 12/6, right? So that would be pi over 6 would be our answer there. Put the negative in front because we're going counterclockwise to get that angle. For C, √2/2, those are easy, right? All of our quarters are √2s over √2s for both the x and the y's, and the signs are just dependent of which quadrant we're in. So where is it positive? It's going to be here in quadrant 1, because I don't care about this side. And where is that? Pi over 4. You should be able to get your quarters pretty good from your unit circle, depending on what the sign is. When you're asked to estimate, just grab your calculator and estimate it. Do make sure that your mode is in radians. The only time you would have it in degrees is if you're specifically talking about degrees or you see the degree symbol there. So we're going to just do a second sine, what was it, 1/3? So 1 divided by 3. And gets me about 0.34. So I'm going to say approximately 0.34. Okay, so we got all of those from the unit circle or our calculator. All right, so now let's jump to cosine. So cosine, let's go ahead and plot that. Let me scroll this up so I can get it all in there. Cosine, remember, starts at a y-intercept of 1. So y-intercept, x-intercept, minimum, intercept, max, intercept, minimum, intercept, minimum. So there's our cosine curve. Not 1 to 1. So we're going to go ahead and restrict it. So again, what's our range? It's the same as the sign, -1 to +1. So what value are we at -1? Well, I'm at a -1 here. What is that value right there? That's pi, right? Pi. This would be at 2 pi. So we're at pi. Where are we at +1? We're at +1 up here at 0. Oops. 0. So I'm going to restrict my graph between 0 and pi. So right there is the part of the function that I'm curious about. So we're going to make our domain of the inverse be the range of the original, so -1 to 1, which then would restrict my range to be 0 to pi. Okay, so let's go ahead and evaluate these using our unit circle. Oh, I didn't graph it. Come back, let's graph it. Oh, I ran out of space there. Quickly do a graph of that. So again, we have our ordered pairs. We were at 0, 1, so the inverse of that would be 1, 0. I'm just going to put 1 here, spread it out, -1. And then we have, what else? We had, oh goodness gracious me, I can't think. We were at 1 and pi, or 1 was that pi? No, it was 0, 1, and it was negative. It was pi -1. Couldn't think for a second. Pi -1. So the inverse of that would be -1 pi. So -1, we're up at pi. So I don't know, where do you want to put pi here? Let's put it up. Let's cut it into quarters, 1/4, 1/2 pi. Why not? Let's stretch it out. So -1 pi. Okay. So now, where was that x-intercept occurring at? The x-intercept was at 1/2 a pi 0, so that inverse would be 0, 1/2 a pi, which would then be your y-intercept. So we'll put that there. And then we would have our curve like this. Okay, so there is our cosine inverse graph. All right, so now, again, let's use our unit circle and use our process about inverses. So if I set that equal to y, then that means that the cosine of y is going to have to be equal to 0. So cosine, remember, is x, your x value. And we are restricting between 0 and pi. So that gives us quadrant 1 and 2. That's where we're between 0 and pi. So we're looking for, when is it 0? So when is my x 0? Or no. Yeah, my x is 0. I don't know why I was thinking there. My x is going to be 0 up here, right? At 1/2 a pi. 0, 1. When is my cosine -1/2? So looking at my unit circle again. So my cosine is my x. We're going to be definitely in quadrant 2. So that puts me at -1/2 √3/2, which is 2/3 pi's. So 2 pi over 3. √2/2, that's an easy one again. Pi over 4 has to be in quadrant 1. And then using our calculator for cosine inverse of -1/3, 1 divided by 3, enter, 1.23. So approximately 1.23. Okay, there that be. Tangent. All right, so let's go ahead and plot our tangent function. I guess that's good. I got everything there. So tangent, remember, has a point of inflection at the origin, has a period of 1. So my asymptotes are at every 1/2 a pi. If it was cotangent, then it would be shifted over and your asymptote would be at 0 in every pi. And then at 1/4 of a pi, we're up at 1. -1/4 of a pi, we're at -1. And then I can keep doing that a bunch of times. As many as I want. Or as many as I can make. Alright, so definitely not 1 to 1. So what we could do here is we can restrict our domain just to 1 period. Right, because if we just stuck to 1 period, then I would definitely pass the horizontal line test. So we're going to stick to the interval -1/2 a pi to +1/2 a pi. So that's that middle chunk right here for our domain. So my range, or my domain for the original would be my range for the new. Your domain for the original your range for your original would be your domain for the inverse, right? So my range for the original is all real numbers, which makes my domain for the inverse all real numbers. And we're restricting the domain of the original function to be negative half a pi to positive half a pi. So that's going to be your range of the inverse. So what does that look like? All right, so what do we have happening here? We've got 0, 0 still there. At quarter of a pi, we were at 1. So the inverse of that would be 1/4 of a pi. And we're going up to half a pi. So half a pi and down to negative half a pi. And that's going to be asymptotes, sort of bounded above and below by that. So at 1, we're at quarter of a pi. So that negative 1 would be at negative quarter of a pi. And then we'd have this curve happening like this. So there's our inverse tangent function. Okay, so using the same concepts as before. So this time we're sticking to negative half a pi and half a pi. So that puts us in quadrant 1 and 4. And x can be all real numbers, right? So if we set this equal to y, then we have the tangent of y needs to be equal to 1. So remember, tangent is y over x. So for a ratio to be equal to 1, they have to be exactly the same. And they're exactly the same at root 2 over root 2. And at negative root 2, but we can't be in quadrant 3, so that's no good. So where am I here? Quarter of a pi. Over to B, we need our ratio to be negative root 3. So again, our options are, we have 1/2, I'm ignoring that negative right now, and root 3 over 2, or root 3 over 2 and 1/2. If I do y over x here, that would be root 3 over 2 divided by 1/2, which is root 3 over 2 times 2 over 1, which cancels. So that does get me to root 3 over 1. So this is the one I want. I don't want that second half because that would get me a different ratio. But now I need it to be negative. So remember, we can only be in quadrant 1 or quadrant 3. Well, they're all positive in quadrant 1. So that means that I have to go down to quadrant 4. So now going to my unit circle, I'm looking for 1/2 and root 3 over 2. It's going to have to be a positive 1/2 and a negative root 3 over 2, which puts me down at 5 pi over 3, not between negative half a pi and pi over 2. So that means I have to get the negative version of it. So how many more thirds do you need to make to get to 6/3 pi over 3, but give the direction, so negative pi over 3. When is tangent 0? So tangent, so that means it would have to be 0 over 1, which would be 1 comma 0, which is 0, right? And then estimating tan inverse of 5. So second tan inverse of 5 is about 1.37. Again, I hope you're pausing this at any point in time to get your thoughts going. Okay, so now the next example has us doing a whole bunch of calculator work. Instead of me flashing back and forth to write the answers down, I'm just going to go through it, and then you can write the answers straight from the calculator. Again, if you're not getting the same answers that I'm getting on my calculator, make sure that your mode is in radians and not degrees. So for 4a, we're doing sine inverse of negative 0.74. Hit enter, and you get negative 0.83 if I go to 2 decimal places. B, cosine inverse of 1.5. Right there, that should be a red flag. Because remember, my x needs to be between negative 1 and 1 for my domain. So, yeah, domain error right there. It gives it to you. So write undefined for B. It's undefined. C, second sine of sine of 2.36 pi. Close all those parentheses. Gets us about 1.13. And then tangent, so tangent, second tangent of -4. Close all that. Gets you -4. Okay. All right. Got that done. So now let's go ahead and evaluate without a calculator, and we're going to try to do this without pulling up my unit circle and cheating. Now we already kind of know these answers, so let's show you how we would get it without directly looking at the unit circle. So cosine inverse of root 2 over 2. So my first thought process is my cosine is x. So I'm going to just recreate this again. So where are we at root 2 over 2? Here. That's where it's positive. It's also positive down here at root 2 over 2. But remember with your cosine, we can only be in quadrant 1 or 2. So that puts me here, which can't be in quadrant 2, so we're at pi over 4. Your tangent, again, we would do that same thing and try to figure out what the ratio needs to be. So this needs to be of the form -1/2 root 3 over 2. So now how do I do that without looking at my calculator? So remember, sine is, oh goodness gracious, sine is y over x, opposite over hypotenuse. So that makes this become the root 3. Actually, no, that would be adjacent, right? Do I have that on the wrong, did I do the wrong one? Oh goodness gracious, now I'm going to look at the unit circle and do this differently. So I need it to be y over x. Yep. And my cosine is adjacent, so this would have to be 1. Oh goodness, someone shout at me. It's not -1/2, it's +1/2. I'm like, why does that not work out? It should, okay, negative root 3, right? Hypotenuse is 2, that's 1. Root 3 is the longer leg of this 30, 60, 90 triangle, so that would put it opposite of the 60 degrees. Okay, so that means that my angle is going to be 60 degrees. How do we go from 60 degrees to radians? Multiply it by pi over 180, right? 60 divided by 180 is 1/3. So pi over 3, and since we went clockwise, it would be -pi over 3. And then for C, my brain still hasn't quite gotten this one out. The answer is 1.1, which would make sense because the cosine inverses and cosines should take care of each other. And because I think it's symmetrical within the over the x, that would go to positive. My first thought was that it would just be -1.1, but it's not. It's positive 1.1. So I need to think some more on that, and then I'll get back to you guys and we can talk about that one tomorrow in class. If anybody wants to take some time to get their brains through that one, feel free. Okay, so anyways, now let's go down to exact values graphically, which is kind of what I was doing. Because I'm a visual person, that's just kind of what I usually intend on doing. Okay, so we're going to work inside, and then peel our way out. So the sine inverse of -1/2. Okay, so let's first think about what that looks like as a reference angle. So sine inverse means we're always trying to find the angle. So we're trying to think, let's let theta equal sine inverse of -1/2. So sine is opposite, so opposite of theta is going to be -1. Hypotenuse is 2. Using the Pythagorean theorem gets us that other leg to be root 3. Okay, so all we did was we did a 2 squared is equal to -1 squared plus x squared, which got us to root 3. Okay, so now we've got our reference triangle set up. So now I'm going to substitute in place of sine inverse of -1/2 actual theta. So what is the cosine of theta of this reference angle? Well, cosine, remember, is adjacent over hypotenuse. So it would be root 3 over 2. Okay, so let's do the same thing for number 7. So cosine inverse of 5/13. So that's going to put me up in quadrant 1. Here's our theta. So I'm going to let theta equal cosine inverse of 5/13. So opposite is sine. So this is going to be 5 here, 13. Pythagorean theorem. 13 squared minus 5 squared, square root it, gets us 12. Pythagorean triple, maybe you identified that one. So then the sine of theta would be equal to opposite over hypotenuse, which would be 12/13. Will be your answer there. Pretty cool how that works out. Okay, last one. Good old word problem. Okay, so let's get our brain wrapped around what's happening here. We have the bottom of a 20-foot replay screen at Dodger Stadium is 45 feet above the playing field. Okay, so here's my screen. It's 20 feet tall. But then it's also 45 feet above the playing field. Okay, so as you move away from the wall, the angle formed by the screen at your eye changes. So we're here, we're moving away. So at one point, like if I'm here and I'm looking up, I can't see what's on that screen, right? Maybe I can't see what's on the screen there. Maybe I can start seeing what's on the screen there. So there's kind of that threshold of where that starting point is, where you can actually see what's on the screen, right? So now we keep moving away. The further I move away from that screen, the angle of what I'm looking up decreases, right? So the further away I am, the less I have to look up. So as I move away from the wall, the angle formed by the screen of your eye changes. There's a distance from the wall at which the angle is the greatest. So I need to figure out which distance, okay, from the wall, so the distance away from the wall. So what distance is it where my angle to look up is the greatest? So everybody kind of see what's happening there? Okay, so now I'm going to recreate this triangle. I'm going to erase that. So this is what we have happening. We've got a triangle, right angle. This whole entire length is 65 when you add it together. Top half is 20, bottom half is 45, right? We want to find this distance x. Okay, so we've got two different angles happening. We have theta. We want theta to be the greatest angle that we would need. So the greatest angle, let's say, is right here. So we'll call that theta. And then you have two different angles happening. You have theta 1, which would be the whole entire angle of that triangle. You got theta 2, right? So what are my relationships? Well, theta, right, which represents, so I'm going to let theta be the greatest angle. Okay, well that would be equal to theta 1 minus theta 2, right? And now what are our equations to solve for theta? Well, remember, to solve for an unknown angle, we use inverse trig. So if I wanted to solve for theta 1, that would be opposite over adjacent. So we would do a tan inverse, the opposite leg of this whole entire angle of that big triangle, this triangle right here, opposite leg is 65 over our unknown x. Theta 2, right, is this little tiny triangle right here. Oops, not in highlighter mode. Okay, that opposite is 45 over x, so tan inverse of 45 over x. Okay, so why do I care about that theta 2? Well, that's taking away, that original angle where I won't be able to see the screen, right? That gets me really close to the wall. Okay, so now I have to erase this, give myself some space. Hopefully you have that. What we're going to do is theta then is going to be equal to, so let's plug that in. We said it was theta 1 minus theta 2. So the tangent of -1, 65 over x, minus the tangent inverse, I don't know why I said -1, of 45 over x. Okay, so now that's a pretty complicated equation to solve ourselves. So we're going to rely on the calculator to do that for us. So I'm going to go over to my calculator. I'm going to graph that. So here we go. So we have tan inverse of 65 divided by x minus tan inverse 45 divided by x. And I just remembered I want to make sure I have this in degrees because this whole problem is talking about degrees. Probably would make more sense if we were talking in degrees as opposed to radians. Okay, tan, did I get it into degrees? Yes, I did. All right, zoom 6. All right, so we've got that. Not really showing me a whole lot in there. So what I'm going to do is I'm going to change the window of this. So I can go ahead and hit window. I know that I can't have a 0 distance or negative distance. I'm going to make my minimum 0. I'm going to make my max 400. Just play it safe. I can't have a 0 degree or negative degrees. I'm going to change that to 0. And I'm going to change this, let's say, to 16. I just played around with these prior to doing the problem, so I know what will make it look good. All right, so there's our graph. So you can kind of see here, this represents, so as we're going x, right, x represents my distance that I am away from the wall, and my y represents the angle that we're at. So here I am getting to a point, there's my highest angle, right, and then it decreases down. So I want to find that maximum value. So my calculator can do that for me. So I'm going to hit second trace, maximum. I'm going to have to move all the way over to the left of that max, hit enter, move to the right, hit enter, and there is our ordered pair. So our answer is going to be, so here, I guess we'll do this. Look at the graph on there so you have it. So it looked something like this. And your max was at 54.083 and 10.475. So when you stand about 54 feet away from the screen, the angle is greatest at 10.48 degrees. There it is. All right, that concludes your notes, everyone. Bye.